Sorry, it's a bit grainy there, but all it says is something that was in the notes from last time. The major new effect that comes from the complete set of Maxwell equations is that long after all activity at the source has completely stopped and all charges and currents are zero, the block of field continues to travel through space. And this is one of the great things about having put together the four differential equations. We end up with wave-like solutions of electricity and magnetism. So, and I gave the analogy that if I was to shake, and we went through this in some detail, shake the charge, a sheet of charge, I can then restore and shake it up and down. Well, from the second shake, the block of fields doesn't catch up with the first one. They are both travelling at the speed of light, fundamental constant. And so the block of fields, of electric and magnetic fields, continues to travel through space. Now, today is a kind of bridging passage, if you like, between the electricity and magnetism part of the course and the optics part. It's going to be mainly to explain a series of approximations that we're going to use. Now, the first one is that we are going to consider these plane waves that we studied in lectures 11 and 12. Now, of course, we don't actually, when we transmit radio waves or television waves or from your mobile phone to the local electromagnetic kind of masts and so on, we use wires, we use aerials, we drive electrons up and down aerials. So first of all, let's just take a look at how one sets that up in practice. We're not going to be worried too much about practice. Let's say we've got some signal generator which produces some kind of well-defined frequency. An example which I'll continue to use because it's a nice easy one, because the speed of light is 3 times 10 to the 8 meters a second. So if we choose a wavelength of 300 meters, which is about in the middle of so-called medium wave for radio transmissions, then we've got about 1 megahertz. So let's say we're driving electrons up and down this circuit with 1 megahertz. In practice, what you do is you would have a couple of wires connected in this way, and so in this part of the leg, the electrons are being driven downwards at any one time, and then in this wire, the electrons, of course, it's in a circuit being driven this way. And in effect, there's a small gap here, but basically this thing just behaves as a single wire. Now, I'll come back more to the dipole approximation next term, but again, in a sense, this is already an approximation, is that the wire has to be short compared with the wavelengths for the so-called dipole approximation to hold, and it's only in those circumstances, if the wire is short compared with the wavelength, that the electric field produced is called dipole radiation. So that's there's going to be about 6 brutal approximations today, but I want to study just the principles of optics rather than the practice. So it is worth just, of course, mentioning at the beginning, in practice we generate EM waves, and this is, obviously, when you see a TV antenna or a radio antenna, it's not a great sheet of metal, it's a clever arrangement of wires, but we generate EM waves by driving charges up and down wires. And this, of course, is illustrated in figure 57 of the course handout. And we're going to completely ignore that in practice, AB is not usually a single wire because it's effectively going to behave like a single wire with charge being driven up and down it. So it's sort of like approximation 1. I'll put the maybe a star. This is number 1. You'll see there's quite a few coming. If the wire is short compared with the wavelength, and obviously we don't tend to use 300 metre long wires where, you know, a typical radio transmitter. I'll bring one into the next lecture. You're talking about something which is definitely less than a metre. And so this would be very good approximation for an ordinary size mast broadcasting in the medium wave. But if the wire is short compared with the wavelength, the electric field produced is called dipole radiation. We'll look at static dipoles, electric dipoles next term when we study dielectrics, and we'll study this the nature of this approximation in more detail. At the moment, let's just take for granted that we accept this approximation, and the dipole radiation field that it produces is shown in figure 58 of the course handout. So this is the field of dipole radiation. Now, again, one of the things that I think is very important to understand is that the field now is not just spreading out homogeneously over the surface of a sphere. And that is that, first of all, I'm only going to, and we'll come to this as well, from now on, I've mentioned this, one of the many, many approximations, we're going to have a direction of propagation and consider an electric field vector oscillating at right angles to it. We know that in a true electromagnetic wave, there's a direction of propagation, an electric field vector and a magnetic field vector. But because for a start drawing things gets very difficult, we're going to simply throw away our magnetic field vector and just concentrate on the electric field. And it is indeed the electric field that interacts most strongly with matter. Again, we'll be studying that next term. Now, what this is illustrating, figure 58, is that the G in the centre, let's imagine that that's a generator, and we can just think of it as a wire. Yeah, like, and we're driving charges up and down, and the detector D is also just a wire, and we're driving charges up and down in the wire. The electromagnetic wave goes from G, and then we detect it. Well, the problem is circularly symmetric. In other words, it's excuse me, I think I've labelled this this up not very well here. This should be latitude. I was going to do the globe analogy, so I scribbled this on the view graph, scribbled the wrong coordinate. It's circularly symmetric in the sense that anywhere around the equator, if I put the wire anywhere, imagine at the centre of that globe there's a little wire, yeah, which is, we're driving charges up and down it, and here I put a detector. Well, it doesn't matter anywhere that I go around the equator of the globe, I'll get the same result. So it's symmetric with respect to longitude. However, because of the particular feature of electromagnetic waves, and this applies throughout, that we've got the electric field vector is perpendicular to the direction of propagation. If I place my detector at some higher latitude, I don't observe the same electric field. You get here, you can see the detector has to be oriented. If I want to drive remember, at this angle, let's say we're coming out now at some higher, you know, like York is about 50 degrees north of the equator. If you through the globe, we're coming out through York. The electric field has to oscillate perpendicular to the direction of propagation, and therefore we observe, if you like, and the charge is oscillating up and down at the origin. So the electric field is being oscillated up and down vertically at the origin. If we observe here, we only observe the projection of the electric field at that longitude until finally, if we come out, the globe's tilted of course, but let's pretend that the North Pole is vertically up. At this point, there's no projection. Remember, the electric field is oscillating in this way. It cannot have a component along the field direction. My electric field's oscillating up and down. This is the field direction. Well, the Maxwell equations tell us that it's got to be perpendicular. So there's absolutely no signal at all out through the pole if I'm oscillating in a north-south plane. So that's what's being illustrated in the figure here, is that if you like, you see this is a big arrow here, I get the maximum signal coming out through the equator. I get the a smaller signal, and I have to orient to get the maximum signal, I have to orient my detector perpendicular to the direction of propagation, because that's the way the E field is behaving, until finally, if this generator is driving up and down here, well, there's no, you can see that it's a null field here. The field is getting smaller and smaller towards the poles until it actually disappears at the North Pole. So the real field of an oscillating charge with the energy spreading out in 3 dimensions is not spherically symmetrical. So that is what gives us problems in studying dipole radiation. But it introduces a lot of difficulties, mathematical difficulties, without giving us any real new insight into electromagnetic waves. So in the optics part of the course, we're going to you can view the approximation in 2 ways. You could say, well, we're just going to stick in the equatorial plane, or you could say we're going to consider plane wave sources. It amounts to the same thing in practice. So I'm not hiding from you today. We are going to be sweeping a few things under the carpet, and this detailed behaviour of the dipole radiation field is one of them. So the main feature, and it's only the main feature, not the only feature. As shown in figure 58, there's a strong latitude dependence to the radiation. But the main feature is that the wavefront spreads out over the surface of a sphere. In other words, if we integrate all the energy over, again, maybe it's too trivial for you at this stage, but of course it's A is 4 pi r squared. Somehow the energy is spreading out over the surface of the sphere. Not homogeneously, but in the end, if we surround the source with a sphere of some radius r, all the energy's got to be passing out through it somehow. So that's the main feature. And so, again, this is a bit of revision. I'm going to do a bit of kind of waves revision in general today, because we're moving on to this part of the course. For any wave, the intensity and for light, there's a special word for intensity. When you look at optics book, like for example, I recommend Hecht's book on optics. The Feynman optics is too simple. Now that's was for first year sort of students. I'm going to be recommending Hecht's book on optics, and the intensity of light is specifically called the irradiance. It doesn't mean anything different from intensity for electromagnetic waves. It just means intensity of an EM wave. As opposed, you wouldn't say the intensity of a wave on a string was irradiance. It's specifically for light waves or EM waves. The intensity is proportional to the square of the amplitude. And again, it's a long time since you did Phil's Vibrations and Waves course last year. That's in the Young and Friedman textbook, chapter 15. This statement has got nothing whatsoever to do specifically with electromagnetic waves. The intensity is always the square of the amplitude of the wave. So the, excuse me, for EM waves, again, this is also something I'm going to come back to later in the course. The intensity, this is now specifically for EM waves. The intensity is equal to, I'll define this symbol in a minute, it's actually what's called the Poynting vector, is equal to epsilon naught c times the average of the square of the electric field vector. which itself is now equal to a half epsilon naught c E squared. Let's make this equation 13.1. So I'll just make the board note and then discuss it in a bit more detail, where S is the Poynting vector Any of you read New Scientist? Any New Scientist readers out there? Good, there's one or two. Well, they have a lovely little bit at the back called nominative determinism. And this is the correct spelling. There's an American scientist called Poynting. But it's rather nice that in the electromagnetic field, the Poynting vector points in the direction of energy flow. So it's very easy. He got the right name. It's very easy to remember. The Poynting vector points at the direction of energy flow in the electromagnetic field, and its units are joules per square metre per second. It's telling us how much energy, we've had this with current density, how many coulombs are flowing per square metre per second. If we had a heat flow vector, it would also be how many joules per square metre per second. And the Poynting vector, it tells us how many joules per square metre per second are flowing in an electromagnetic wave, and this is, and E naught is the magnitude. And again, I'm sorry, at the moment I have just plucked this formula completely out of the sky. But just to mention, as a kind of note, equation 13.1 is proved in lecture 24. We're going to do the energy topic towards the end to bring everything from electromagnetism and optics together, electrical energy, magnetic energy, energy in electromagnetic waves. For the time being, you've just got to accept it. Of course, this step to this step should be easy, because if the electric field is oscillating as a cosine, which is an example of a wave, well, clearly the average of a cosine, if I take the average of E naught sine something, and come to what the something is, over a period, then E naught squared sine squared averaged over a period. The average of sine squared, trivial integration for you, at your level is a half, and so we can express that as a half E naught squared. And I should say too, this does include the energy being carried by the magnetic part of the wave. Yeah, so this formula is correct, and we'll come back to it. The crucial thing, though, is just that the energy is spreading out over a surface of r squared, and therefore, thus, let's just, this is the important bit. Oops, wrong way. Put this back. Thus, the electric and magnetic, it is an electromagnetic wave, even though we're going to concentrate on the electric part, field amplitude must decrease as 1 over r. In other words, our wave function that satisfies spherical waves is a function of r minus ct over r. And we'll make that equation 13.2. And this type of wave is illustrated in figure 56 of the course handout. So as I said, we're going to brush away this complicated angular dependence. The main feature is that the energy of the wave is radiating out over the surface of a sphere. So therefore, by conservation of energy, as the sphere gets larger and larger, the intensity has got to be dropping off as 1 over r squared. And if the intensity is dropping off as 1 over r squared, the amplitude is dropping off as 1 over r. So we must have, this is a crucial difference to the plane waves, and one that we must bear in mind when we look at the actual amplitude of the wave. So the spherical wave looks like this. And to emphasize too, when we look at waves, I've emphasized before, we've still got, you know, like for a plane wave, we just had a function of x minus ct. And I explained, and coming back to this, it's just a fixed pattern, it moves in space. And there are two ways of looking at it. We can either, if you like, take what you might call snapshots and then study as a function of r, or we can, like, so, you know, let's say we've got an absolutely perfect sinusoidal wave. Well, clearly, if I just take a snapshot of the wave, and let's imagine for the time being it's just a wave on a string, and we can really actually see, if we shake the source sinusoidally, it sends out sinusoidal waves. If I keep shaking, and that's exactly what they're doing, you know, in Radio 3, they're shaking the source at 1 megahertz, and the carrier wave is just coming out as a smooth sinusoidal wave. Well, clearly, if I take a snapshot at any time in space, I see it a sinusoidal oscillation. But also, I could say, well, if I instead just stand at one place, in other words, I fix R and see what goes before me, just fix R and a plane wave goes in front of me, I see an oscillation of the electric field or the piece of string going up and down sinusoidally in time. So I can, and we can't represent on view graph space and time at the same sort of view graph. So and this is of course a convention for representing waves. Here we've got a spherical wave which is spreading out from the origin, and this is the crucial point. Its amplitude has got to drop as 1 over r. It's still spreading out at a velocity of c. We've still got the same type of numerator that we have in plane waves, but the amplitude is decreasing as 1 over r. And because the amplitude is decreasing as 1 over r, this is like, let's say I've made a pulse. In other words, instead of sending out a whole sinusoidal wave, I've kicked the board up once, not at an infinite acceleration, and then I've, you know, sort of gradually moved it up, and then I kick it back down again, and it sends out a pulse of this shape. Well, because of the 1 over r dependence, if I take a snapshot of the whole wave at t1, t2, of course, it's moved this distance. You know, between this time and this time, between the time of the two snapshots, it's moved from R1 to R2. But unlike our plane wave, it's decreasing in amplitude. And because of the 1 over r variations, also getting slightly distorted as well. Because 1 over r is not quite the same here as here. 1 over r here is not quite the same here as here. So even if we neglect the complicated angular distribution, we've also got that the wave distorts. So that's representing the wave as a function of r, taking two snapshots at time t is 1 and t is 2. And if I look at I can look at the same thing, it's shown in figure 58b for a spherical wave. I could simply show it as a function of time for a couple of different distances. So that's what it looks like at this distance, that's what it looks like at this distance, but now I'm plotting as a function of time. And of course, because of this symmetry between r and ct, I get exactly the same thing. So we can't represent on a transparency space-time. So keep an eye on what's being plotted always. But the important thing is always this 1 over r dependence. So that is something that we are going to neglect. Now, would you like to hear one of my rambling anecdotes? Yes, you would, wouldn't you? Well, last summer I was on holiday in Italy, and I happened in a very crowded square to sit down next to an engineer from the Netherlands. You know, they were very polite. All the tables in this little sort of, piazza were full, and overheard these people speaking English. I thought, oh, well, these Dutch people usually speak very good English, and he was chatting with an English friend. Do you mind if we join? Oh, yeah, please do. And it so happened that his job was to make sure that there are no dead spots for wireless broadband anywhere in the Netherlands. But you don't want to build too many masts to re-amplify the signals. You see, in this case, the wave is decreasing in amplitude and getting distorted. So if you want to pick up wireless broadband everywhere, you've got to at some point absorb that wave and then re-radiate it from a radio mast. Now, you don't want too many of these things because it costs money to build them. People are worried about it's going to fry their brains, whether that's true or not, slightly different. But basically, nor do you want to have any dead spots. And so you've got to allow for the fact that real waves are spreading out, they're getting distorted, and their intensity is decreasing. And I said, oh, I teach the Maxwell equations, you know, it's a university, and you know, we got chatting about, you know, said, I bet you earn a bit more money than me. And I realised he earned about, you know, 2, 4, 5 times as much. But he deserved it. He was solving the real thing. I'm just saying, oh, we got a plane wave, and he sort of went, you know, plane wave. Now, if you want to, I mean, he was earning like, you know, well over 100 grand a year, and if you want to earn that kind of money, you've got to solve 3-dimensional dipole radiation. You really got to do it. But if you just want to pass exams and kind of like, you know, listen to some lectures, we can stick with plane waves. So I am going to, again, you know, I'm being honest with you, we're brushing a lot of stuff under the carpet here, but at least I'll be honest that we're doing it and say, put it in this way. So let's move this up a bit. Because of the mathematical complications, approximation, horrible approximation 2, being honest, we're not leaving it out for any other reason that we want to be able to study electromagnetic waves relatively easily. Because of the mathematical complications of studying spherical waves, we've got the directionality problem, we've got the 1/r decay, which causes distortion and loss of amplitude of the wave. That because of those complications, from now on, we will study mainly plane waves. There are a couple of things, like when we come to what's called Fresnel diffraction in optics, where we really, you know, if you throw away the spherical nature of the wavefront, you lose all of the information. And there are 1 or 2 little bits where we will have to consider spherical waves. But mostly we will study plane waves. We will study mainly plane waves. As I say, we will have to consider the spherical nature of the wavefront at a couple of points in the course, but mostly we're just going to say, oh, psi is some function of x minus ct. So we'll make this equation 13.3. And don't forget where psi, I mean, this was in lecture 12, but I'm going to restate it because it's very important. It can stand for E, any component of the E field, can stand for any component of the B field, and in the Lorentz gauge, where the phi and A, the equations for phi and A separate, it can stand for any component of these, and so as described in lecture 12. So if you like, of course, if we shake an infinite sheet and this block of field travels, theoretically its amplitude won't decrease at all. As it goes through the lecture theatre and sweeps past all of you, it'll have the same amplitude. So we're missing out on some realities of dipole radiation. But this makes the maths a lot easier, particularly next lecture we're coming on to interference, and the following lecture to diffraction. And interference and diffraction of plane waves are relatively easy, and interference and diffraction of spherical waves are much harder. Especially you'll see that around lecture sort of 17 or 18 when we look at those. So, horrible approximation number 3. You'll think that there's, you know, what we're doing is totally unrealistic, but obviously we wouldn't make these approximations if they still didn't have some, you know, physical reality. As a further simplification, we will consider only the electric vector E. And again, next term we'll have to revisit this slightly when we study magnetic materials on the understanding that the B field is perpendicular to the E field and of course the propagation vector, the direction of propagation. So we're going to look at plane waves and we're going to concentrate entirely on the electric field. This one's not on the course handout, this was just something that I took from I think an Open University material. So in that example that we had last week, we had a wave propagating out in the x direction, an electric field vector oscillating in the y direction, and this is, if you like, one of these so-called snapshots of the wave, and we see the electric field is oscillating in the y direction, and we're assuming that there's a magnetic vector oscillating in the z direction, but the magnetic vector is not shown. So again, it makes diagrams horribly complicated if we try and show everything all the time. So almost everything that we're going to do, just remember it's in there, but we're just going to say, oh, this is an EY oscillation, and this is X propagation. In other words, my K vector's in this direction, my E vector's in this direction, and my neglected and forgotten B vector is along the Z axis. Ready for horrible approximation number 4? Of course, if you, like this lamp, is a typical ordinary incandescent light bulb or a candle, you get bursts of what are called coherent radiation, which last for about 1 to 10 nanoseconds. So imagine this is actually just a very hot tungsten wire. Yeah? For about 1 to 10 nanoseconds, it will give off a burst in which the electric field vector happens to be in this direction. Somewhere between 1 and 10 nanoseconds later, it will give another burst in which the electric field vector is still perpendicular. It obeys Maxwell equations. The directions towards you, the electric field vector might be there. 10 nanoseconds later, it gives off another burst in this way. 10 seconds later, and so on and so on. So what we actually see is what's called unpolarized light. In other words, the electric field vector can be perpendicular if the direction of the wave is towards you. The electric field vector can be in any of these senses. So what really happens, again, if we want to consider real radiation, is that you'll get a sort of burst like this, but then you'll get another burst, which is, this might be, that just so happened at that moment we got one along the x-axis, an electric burst on this axis, but the next one comes out with random phase. You know, let's say the peak of this one and the trough of this certainly don't coincide. It's got a random phase, and this might happen to be along the z-axis or anywhere between the two. So we can, however, with lasers, and certainly we can do it with signal generators, we can arrange for the electric field vector to be perfectly polarized. In other words, really along one axis. And similarly, with a laser or with a signal generator, we can keep this thing constantly in phase. In other words, it kind of goes on and on and on and on and on. We're not getting lots of little bursts with different phase. And we're just going to consider, he says, this is yet another approximation that we've got a perfectly, what's called coherent, plane polarized source. The electric field vector is exactly on the y-axis, for example, and the radiation comes out completely coherently. And that is actually a good approximation for lasers, and certainly with a wire controlled by a signal generator. For low frequency electromagnetic waves, we can just choose it quite easily. So it is, however, yet another approximation. So let's say that. If you like, this will be approximation 4. we will also restrict attention. We will come back to release this because again there are some effects where averaging over different polarizations is important. However, mostly we're going to restrict attention excuse me, to the case where the E field oscillations are along one axis only. So we're now cutting down to something of this form that we're going to have, let's call that, because we did it in our first example as the y-axis, let's stick with the y-axis. And now I've shaken a charge up and down the y-axis and a wave of electricity goes out along the y-axis. Well, it will have some amplitude E0 and it'll be multiplied by some function x minus ct. So this is equation 13.4. And in practice, what this corresponds to is our study of optics is, again, mainly we will have to release this approximation once or twice because there are some ideas where having different polarizations is important, particularly when we study, for example, Brewster's angle of getting polarized light by reflection from a surface from unpolarized light. Obviously, when we consider problems like that, we'll have to release this, but mainly restricted to plane polarized waves. So, just to emphasize, because again people get obsessed with the idea that waves are sinusoidal, the wave can have any shape. And this is illustrated in figures 49 and 53 of the course handout. So what these figures are illustrating now is restricted to these plane polarized waves, but of course they can still have any old shape. For example, when we did one of the two ways we did the unification theory calculation, we had if you like, a wall, a burst. So what that corresponds to is that I've kicked the source up instantaneously. I get a wall of electricity. If you like, you might be worried about an infinite acceleration or deceleration, but it's just a kick. And that sends out a wave, and that kick would give me this characteristic square shape of wave coming out. If you like, it's a sort of instantaneous infinite acceleration at the origin. It's like in mechanics where you have a kind of constant, you look at a collision, you have a kind of infinite force at the moment of collision. Likewise, we then sent out a block wave with different polarization and we were left with this block of fields travelling. That would then correspond, the second wave, I now make an infinite sudden downwards acceleration. And so if I have a sudden acceleration followed by a sudden deceleration, the wavefront that I send out, remember the source has now been restored to its original situation, the block of field is square, just because of the infinite accelerations of the source and its deceleration. Similarly, in figure 59, well, this would correspond to me kind of, if you like, shaking the source, much more gradually accelerating it, and then for some reason I decide to decelerate it a bit, accelerate it again a bit, and then decelerate, and actually go the other way, put the ball actually down through its starting position, then whip it back up again. This will send out a wave of this shape, and at a certain time t later, because we're not losing, we've not got any 1 over r decay, we're in our plane wave approximation, I get exactly the same shape except it's moved away from the origin. Of course, if I shake the source sinusoidally, then I send out sinusoidal waves. And again, a lot of the time we will study sinusoidal waves because we've got a lovely easy function to work with. So rather than, remember, this function can have any shape, but we're going to study mainly sinusoidal waves. Approximation number 5. No, it's important to realise that, you know, and indeed this is the whole principle of electromagnetic signalling, is that I control the amplitude and the frequency with which I shape the source. So I determine the shape of the wave, and then when it hits a wire, you know, 300 kilometres away or wherever, it produces the same oscillations in the wire at the other end. And so that's, if you like, the principle of electromagnetic signalling, is that we can determine this wave shape. It travels along maintaining its shape, and then when it hits a wire and gets absorbed, it will produce the same effect at the other end, because the wire is, it can be considered as a generator or as a detector. So that does work, but we are going to consider sinusoidal waves mainly. Again, mainly. So 5, this includes sinusoidal waves. Of course, they are an example of waves of the type E is equal to E naught. And again, some people prefer, and I'm going to use both in different lectures, sometimes to illustrate points, cos kx minus, I can always choose my origin of phase to make it either a pure sine or a pure cosine, or E, and of course this is the best way of doing it. Now, I mentioned this right back in maths lectures last year, that the Euler relation is the most useful I did in that whole course, that e to the I theta is cos theta plus I sine theta, where k is 2 pi over lambda. This is the angular frequency in space, and omega is 2 pi over t. So, of course, but there's a slight point here, is that, again, we get used to learning that the speed is the frequency times the wavelength, but particularly when I do reflection and refraction, I'd much rather write it in this way, as omega over k. I mean, it's obviously the same thing. This is in per seconds, this is in per meters, this is, and the factors 2 pi, of course, are cancelling. This is the alternative way of writing it that I'm going to prefer. So, again, just to make a little comment here, of course, it's much easier to add up sinusoidal waves. And that's what we're going to do, mostly, is just have two sources producing perfectly plane polarised, perfectly coherent plane waves. And there's still some maths to do even now, you know, when we come to do that on Thursday. So again, I've shown this before, but I can't emphasise enough, as we're going into what's called wave optics, to be aware of the wave equation. And I've already made this quite explicit before, but let me just do it again. If I've got a, oh, that's a bit of a rubbish pen there. Let's see if I've got a slightly better one. Yeah. If I've got some kind of wave of the type cosine kx minus omega t. If I differentiate, it's got some amplitude, we might call this E naught, yeah, we might call it A for an amplitude, but this applies to any wave. If I differentiate that, if I take d by dx of this, of course I just bring down a factor k, and if I, well, change it to minus the sign, I differentiate it a second time, I get to back to the cosine, minus the cosine, but d2 by dx squared of this thing brings me down a factor of k squared times the same wave, yeah? Obviously, if I differentiate it twice with respect to time, I get First I get minus the sine, then I get back to minus the cosine with a factor minus omega squared. Yeah? So clearly my d2 psi by dx squared is equal to, and now I've got my omega squared over k squared d2 psi by dt squared, or in other words 1 over c squared d2 psi by dt squared. So this is obviously one example of a wave that fulfills the wave equation. If I differentiate twice with respect to space, I pull down k squared. If I differentiate twice with respect to time, I pull down omega squared, and therefore the d2 psi by dt squared is just omega over k squared times the second order derivative with respect to time, and it fulfills the wave equation. So it's... Sorry? Oh, thank you. This is... excuse me, yeah, me putting things the wrong way round here. Thanks very much. Yeah. Excuse me. So we've got this example of a wave which gives me the solution to the wave equation. So we're going to be adding up these plane waves in this way. Now there's one or two more tiny approximations that I'd like to make before we go into the optics. Again, as I say, I very much would like you to think in this way. I know you've only just sort of started recently on Fourier analysis, Fourier series and Fourier transforms, and you'll have done more on that by the time we get into the sort of optics proper. But remember, k-space has become very simple for us because we're only having the wave moving in the x direction. So k-space is just the k vector. I mean, strictly speaking, what we should be considering is of e to the I k dot r minus omega t. Yeah? But in the end, k dot r is just kxx plus kyy plus kzz, and if the direction of propagation is along the x-axis only, kx is 0 and ky is 0. But so think in terms of angular frequency in space. Similarly, omega space, rather than pure frequency, I'd rather think in terms of angular frequency in time. We were going to do so-called Fourier optics when we study diffraction, and again replace this c is f lambda in your mind by omega over k is a better way to do it. Later on, for example, I will express the fact that light slows down in a medium. In other words, in a medium the speed of light is reduced by a factor n. N is about 1.5 for glass, 1 1/3 for water. I'll express it in this way, that k is n omega over c. That's a neater way of doing reflection and refraction. So that's one aspect. The nth approximation, where n is becoming now a very large positive integer, is that, of course, this is a solution as well. And remember, in the wave equation, if I differentiate this function twice and I differentiate this function twice, because it's only d2 psi by dx squared and d2 psi by dt squared that comes in, it doesn't matter at all if I differentiate this thing twice, or of course equivalently this thing twice, where I've got a kx plus omega t. Well, I bring down my k squared from the two spatial differentiations, I bring down my omega squared, it solves the wave equation. In other words, if I kick a sheet of charge, there it goes, then there's also a wave goes backwards towards minus x behind the blackboard. And that indeed, I sort of glossed over it when we were looking at it, but I think I did mention in passing when we were studying, if you like, the phenomenological way of deriving the Maxwell equations, that there's not just this wave spreading out to the front, there's a wave spreading out to the back. And of course, again, you've got slightly different behaviour because the current sheet goes up. You can imagine that we've got a wire as part of it. As the current sheet goes up, of course the wave of magnetism was going to the left. Round behind the board, the wave of magnetism is going to the right. The electric field is still in the same sense. So it sends an electromagnetic wave backwards as well, a plane wave. A plane wave goes, just like if my wire's at the origin, of course there aren't just electromagnetic waves coming out this way, they're coming out, well in this sense they're coming out all over, but there's certainly one coming out the front and one coming out the back. If I make this a plane wave, I've got this more general solution. So I'll mention that that is something that we're going to neglect. So yeah, we've got a couple of minutes left, so I will just make our final approximation here. I think we're up to about approximation, what are we up to now, 5, 6? 6, thanks. Sort of run out of board there, so I'll use this one. This is just a note in passing because obviously there's no more difficulty studying a plane wave heading towards minus x than one out to plus x. And any fixed function g of x plus ct is clearly a solution of the wave equation. They're linear equations, so there's a superposition of the two solutions, but we're just going to throw away, we're just going to consider the wave going one way because everything will apply to waves going backwards, if you like. So final approximation, and then we'll be starting off, on, if you like, on the interference and diffraction just with waves going forwards, so to speak. Number 6, so you copy it from there, the general solution to the 1D wave equation is of the form psi is some function of x minus ct plus some function, another function, let's call it g, of x plus ct. I've even forgotten what equation number I've got to, 13.7. Let's move this up a bit. Oops, wrong one. Where g of x plus ct represents a wave travelling towards minus x. From now on, if you like, this is more like approximation 6. From now on, we consider f of x minus ct only. In other words, we're just going to consider waves which are going in the positive x direction because there's nothing new added to the physics by considering waves that go in the negative x direction. Okay, lots of brutal approximations today. We're going to put them to good use on Wednesday. Oh, I should say Wednesday, don't forget we've also got a whole cohort problem class. And at the 9 o'clock lecture, I'll do interference of 2 sources, and then I'll do interference of 5 sources as a problem, and that is an important step in going from interference to diffraction. So the problem class is very much part of the development of this topic.